hopefully as you'll see play posit sides. So this is from one of the play posit videos. I believe this is actually from the first one. So trying to cut through some of this. Oh man, I forgot. Technology is not connected. What we're trying to get at is the atomic structure. So within that first question, we were concerned about our protons, neutrons, and electrons. Our protons and neutrons in the nucleus, electrons outside the nucleus. So you all were writing lovely sentences. That was all I needed. Okay? All we're trying to get an idea of is those big kind of broad strokes. Where the electrons exist outside the nucleus does get pretty complicated. For the most part, we simplify it a whole lot. And that's mostly because of one of the next following slides, and that's that we only look at a very small part of the periodic table. We aren't concerned about the whole thing. But where we're going to see our electrons are really our first and our second energy levels. Now we're actually pushing into a little bit more detail within that content. What we have to remember within those energy levels is that we have different orbital types. So the first energy level, we have an s orbital, which looks like a sphere. Right? There's only one orbital that matches that. That's it. When we go up in energy, we copy the previous order or previous orbital type. So we would have an s that also is a sphere. How would I be able to tell the second energy and the first energy s orbitals apart? I know, challenging first day, getting curveballs. How do we tell the first and the second energy s orbitals apart? Okay, distance, size, which both those terms get a little bit weird, okay, but they work for the most part. Okay, the second energy is higher in energy, which then means it can occupy a larger space than the first energy. Okay, so we can go with that, okay, which is useful because then what does that mean? Our atom starts to get larger. Okay, the next thing we want to be aware of that we could go through to classify them is we could throw a 2 in front. So we call it 2s or 1s. That's a really easy way to differentiate those two. Okay, in this case, we could say it's black and blue. Okay, all we're trying to do is find some way to differentiate those at a very simple level first, and then we could slowly scaffold in higher and higher, energy being our largest differential. The problem with energy is that's not easy for us to visually see. Okay, so we've copied our s, but we have to add one more type. So we add a p-type. The p-type is a little bit more interesting because it follows a dumbbell shape. Okay? Complicated, but what ultimately happens with these shapes is how we solve a big mathematical complex wave equation system that we don't need to stress a whole lot about. But in part of solving that, one of the things that we identify is not just the orbital type, but also its orientation. Okay? Put as simply as we could possibly do. So a ballpark approximation. If I had a sphere and I rotated it, would you be able to tell me that it was rotated? No, it's just a sphere. It just rotates around. So there's really only one orientation that we can make any sense of. The p orbital, however, is a dumbbell shape. Would you be able to tell me it rotated? Yes. So we get orientations for the p orbital that we didn't see for the s orbital. Each of those orientation results in a new orbital. And this is where you might have heard, if you had a more advanced Gen Chem class, that's probably y, x, and z. pz, py, px, pz. Because what they're talking about is the orbitals, that dumbbell shape, just being rotated onto a different axis. That's it. Okay? We've got 7 energy levels, which means we have a whole crap ton of possible orbitals and orbital orientations. Thankfully, we don't care in organic chemistry, and all we do is really sit down, for the most part, at the second energy level. And we're just working with those S and Ps. So when we talk about orbitals, we're really talking about the 2s orbital or our 2p orbitals. And what we need to remember is the 2p have 3 orbitals, 2s just has 1. Okay? Our electrons then go into these. So these are just explaining a possible state. That does not mean there's an electron there. Okay? We could reference the chairs. There are, I'm going to guess, 32 chairs in here. That doesn't mean there's a person in each of those 32 chairs. Okay? So the orbitals just say there's chairs. We would then have to place those electrons. Well, how do we know how many electrons to place? What if I placed one electron? What would that mean to you? That is a challenging question. If I just said I had one electron, ta-da, one electron. Does that mean anything to you? It means it's not a full orbital. That's true. That doesn't necessarily mean it's unstable. It could change its bonding characteristics, but we aren't even to bonding yet. Okay. What if I said one proton? Does that mean anything more to you? If we backtracked, we talked about protons, neutrons, and electrons. I know it was up there like lightning fast. What do protons mean?
Positive charge.
They are positive. True. What does that mean to the periodic table? You're like, I don't have a periodic table. You're right, you don't have one. That's a problem that we probably can't rectify. If I have one proton, I know what element it is. Don't shake your head at me like, yeah, you knew that. You didn't say anything.
Sure. I mean, I thought that's what it was, but I wasn't sure because there's no periodic table.
So one proton means, so you said yes, you know what that means, but do you know what the element is?
I don't have a table, but it's the first.
That's fine. It's the first one, okay. Hydrogen.
Yeah.
So one proton means hydrogen. If we say one electron, does that mean hydrogen? No, because the proton defines the element. Okay, so we could go through and start to make assumptions and say, well, if we're putting in one electron, we mean that there's also one proton. That could get real dodgy real fast. Okay, but typically when we're talking about a diagram like this, we're usually referencing that. Okay, so if we put in one electron, we might be referring to hydrogen. Okay, ground state of hydrogen, zero charge, is going to be one proton, one electron. And if I put in a second electron, we're now kind of making the implied assumption that we've also added a proton, we'd move up to helium. So we could go through and look at an electron diagram and start to predict something about the identity of the element. Okay? It again can become a little bit wishy-washy. Okay? So for instance, have you heard of sodium? Okay? What happens if I throw sodium into a lake? Anybody heard of those? Past chemistry teachers failed you. I understand the internal reference. It does a little bit more than just dissolve. It does make it more alkaline. The sodium, as it dissolves, reacts very quickly with water to form hydrogen gas. It's an exothermic reaction, okay, which means it releases lots of heat. What does hydrogen gas do in the presence of heat? Yeah, it explodes. Okay? So if you throw a brick of sodium into water, it explodes. Okay? How do you guys know about, or what's your confidence level on how muscles function? Anybody know anything about muscle function? A little bit? What can you give me? There is water involved.
Acids, lipids.
There are amino acids, there are lipids. For a muscle to contract and release, what's happening? ATP is being used. Okay. ATP is being used to do what?
Move the muscle.
Not quite. Move ions across a channel. Do you know what those ions are? There it is. Sodium and potassium. So for my body to function, I need sodium. right? Make my muscles move. What makes up 80% of my body? Water. Why am I not exploding? I throw sodium into water, it explodes, and yet I need sodium to make my muscles move. What's the difference?
Intracellular?
No. 1 electron. When I throw sodium into water, it's sodium metal. It's an equal balance of protons and electrons to make up sodium. When we talk about sodium, you said a very key word. When I asked before we said sodium, you said what was moving back and forth? Sodium, potassium. There was another word you said. I'm pretty sure you said. Ions. It was charged. The only way it becomes charged is if we change the number of electrons. Okay? By changing the number of electrons, we drastically change the chemistry of the overall molecule or the overall atom. Okay? So when we go through and look at this, what we could be thinking about is where those electrons are located and how that affects whether they want to react or not. Back to your statement, if it's paired, it's relatively stable. If it's unpaired, it's not so stable, and what does it try to do? We have 2 options. It could pick up another electron, in which case it becomes negative, or what were you saying?
I said steel.
Same thing,
Yeah.
steel per pickup. What's the other option? Get rid of it. Okay, so that particular atom has the potential to get rid of an electron or accept an electron. That's going to change its chemistry, okay, depending on what it's interacting with. So understanding our electron configurations can be helpful. Okay, for the most part, we just kind of say, here it is, and it's useful, and then we move on and just kind of ignore it, okay, which is probably true. We're probably going to do that. Okay, but you need to be aware of this kind of fundamental structure and how the electrons fill out. Remember we said we weren't looking at this first energy level much. We're going to shift up to the second energy level. Okay, and the important piece to get out of this is how many electrons can we get into that second energy level? 8. 2 for the s orbital, 2 for the py, 2 for the px, 2 for the pz. That gets me 8 total electrons. Okay? Those 8 electrons and how they're oriented around the molecule or around the atom, we're still stuck in the atom, okay, are going to change its reactivity. Okay? So, if we're going through and doing this, you could be asked questions about valence electron, ignore that statement. We've got our pretty pictures of what our orbitals look like. Okay? So we draw them as a solid sphere or a solid dumbbell, but seeing this weird dashed thing is a little bit more appropriate. We talked about, well, it gets bigger. It's not really getting bigger. Okay? What we're saying is it has more energy. And if something has more energy, what does it tend to do? For instance, who do you think has more energy in this room? You or me?
You.
Okay. What do we see as a difference between me and you? I'm moving around more. So with more energy, I have the potential to go outwards, but that doesn't mean I'm always outwards. I could be anywhere within that system. Okay? So looking at that sphere doesn't mean we're orbiting, doesn't mean we're jumping around on that dumbbell. It just means I have the potential to be in those spaces. And as we move to higher energy levels, I have the ability to expand outwards. That does not mean I am outwards. Kind of, sort of? Okay. Then we could go back to our periodic table, okay, and you might notice all the way, when we compare it to the periodic table on our wall, that this periodic table is significantly more simple than what we would see on the wall. Why is that? Organic chemists are simple-minded, okay, and we want to deal with that second energy level for the most part. Okay? And so if we look at this periodic table, this gets challenging because you have to remember what all those other pieces are. We're really only looking at 2 sections of our periodic table. We're looking at the first 2 columns as a section. Anybody remember what those first 2 columns were called? The S-type orbital, or the S-type, or S-block. Okay? Why would they be called the S-type? Remember that S orbital? How many electrons could we fit?
2.
1 column, 2 columns. What these are specifically referencing is how many electrons we could put in to get to that individual element. Okay? We move to the next block. Okay? You might be like, well, isn't there this big section in the middle that stretches it out? Yes, there is, and we ignore it because that's a different orbital system that we don't care about. What is this block? The P block. Why do you say P? Do you just know it?
6.
Okay. How many electrons do we say we could fit into the P orbitals? 6. How many columns do we have? 6. Okay. What these are referencing is those particular energy levels in those particular orbitals. You'll note that as we go down the periodic table, first energy level, second energy level, third, fourth, fifth, sixth, seventh, and so on. Okay? There's still a whole bunch of other elements in here that could potentially show up and could potentially mean we have to talk about them. So organic chemists go through and largely ignore those. Okay? And you might still say, but aren't these potentially looking at those more fancy orbitals? They are, except they're in the S block. They are, except they're in the P block. Okay? And not only in the P block, they're at the extreme side of it, which means how many electrons are we putting in to get that chlorine neutral? That was a really hard question. I'm hoping you answer it simply, not the hard way. There, that's the answer I wanted to hear. 1, 2, 3, 4, 5. Okay? Why do we not include this one? What happened when we fully filled the orbitals?
Oh, it's unstable.
It's
Oh,
other way around.
stable.
It's super stable, and that's all our noble gases. So we can entirely ignore the noble gases. But fluorine, chlorine, and bromine want to be like the noble gas, so what do they want to do? They want to add that one more electron, which makes them very reactive, and that can help us kind of centralize that chemistry. As we move into those blacked out sections, we add other orbitals, and those other orbitals tend to complicate things. They're now too far away from the noble gases to make them quite as easy a strict just comparison, and it can become a little bit more complicated. Kind of, sort of? Okay. Big patterns that need to come out of this that we absolutely need to know. And we're going to be constantly referring to these throughout the semester. Okay. One you guys have already hinted at. What was the one that you hinted at as we go down? It gets bigger, size. Remember, little gray area. But yeah, down the periodic table, we get bigger. Okay, we increase in size. Why? Well, we're moving to a different energy level. Okay, that higher energy level allows us more access to spread out. And so we can. So we can increase in size down the periodic table. But if we can go down the periodic table, what else could we do? Across the periodic table. What happens as we go across the periodic table? Okay. This one becomes all sorts of weird, particularly depending on who your instructor was in the past. Okay. Officially, why does it decrease? Let's try and be consistent with our arrows. One thing that we'll get a lot of people saying as we move down our rows is that what happens to the number of electrons? We have more electrons. So it gets bigger because we have more electrons. But that's not true because what happens as we go this way? You also get more electrons. But then that means it doesn't work, right? And that's because size isn't dictated based off of the number of electrons. It's dictated based off of where they are located. When we go down, what happens? We're taking our electron at the first energy level, then the second, third, fourth, fifth. That's why it gets bigger. What happens as I go left to right? This first electron's at the second energy level. Where's that one's? It's still the second. It's still the exact same row. Okay? Which means, to a first approximation, I think you said it, what happens to the size?
Oh, it does decrease.
No, I'm asking you what you said. Don't tell me what I think you said.
Decrease.
You said decrease? Okay, fine. To a first approximation, what happens to the size? Nothing. You're not changing the energy level of the electron. It's going to the exact same energy level. And yet, you're correct, it does technically decrease. Why does it decrease? What else changes?
Protons?
The number of protons. So a combination of the amount of, or where our electrons are located, and the amount of protons changes that dynamic. Okay? To make it 100% truthful, we say that. What did I say about organic chemists?
Simple.
Simple-minded. Doesn't change. Across a row, that change in size is so insignificant, we ignore it. Okay? So if you want to remember your Gen Chem instructor, that's great, great tribute, but this time just add that word insignificant next to Gen Chem instructor. Thank you. Okay? Not a big deal. Okay? So cool, if I now change the size of atoms, that's going to change their interactions with how they move around, so I need to have a ballpark idea of their size. What is another really important trend? You got it. Electronegativity. Okay? So we could go through and look at people and say, size, Mike's big, so he must have lots of money because he just steals it from everybody. Okay? That's not true. I don't do that. Okay? Because it's not just size that demands electrons. It's also the atom's ability to steal those electrons from other things. Okay? And quite frankly, I don't have a good ability at that. Okay? That ability to attract electrons is what's known as electronegativity. And that is also a very important thing to be aware of. Okay? Electronegativity increases that direction. Electronegativity is also a word with a whole bunch of letters. This will be the first and only time I will write it out. Oh, good God. And you will see me write the chi symbol or the X, because that's the standard symbol for electronegativity. Okay? What happens to electronegativity down a column? Okay? It decreases. So unfortunately, unlike size, we do actually want to know that it decreases down a column. Okay? So that means for our importance, or for our sake, fluorine is the most electronegative element on the periodic table. Okay? And on this periodic table, potassium is the least, because it's going the complete opposite direction of those arrows. Kind of, sort of? Size increases down. That's it. We need those trends handy because those trends help to explain a lot of the chemistry that we get within organic chemistry. Okay? Tap out of that. Atoms to compounds, we're going to come back to interactions, bonds, and forces. Okay? That's going to be a huge part in our lab. I would make the argument that 90% of what we do in the lab is intermolecular forces. Okay? So we'll talk about that significantly more there. What I wanted to get to, oh, for the love of monkeys, come on. Whoop, coming back here, is looking at our Lewis structures and how we would put these together. Okay? Which is what I tasked you with in that kind of assignment. What we're talking about is we would look at carbon, okay, with its electrons. Okay, since we don't have the periodic table handy, it might be kind of difficult to figure out how many electrons carbon has. Does anybody happen to know? Carbon?
Were you looking for carbon?
How many electrons?
Oh my gosh, sorry. It's cool. No.
6.
How am I getting this
So the 12 is the number under your symbol. Okay. That number is the mass of the atom. So that's the number of protons and neutrons. Okay. Again, lecture, we don't care, because that's looking at our protons and neutrons. We really only care about the electrons. And that becomes an interesting statement. Why? Why should we only care about the electrons? Well, what happens with a Lewis structure? This is now significantly different than what we just talked about. What we just talked about was individual atoms. But now what have we done? We're bringing more atoms near each other. Is that going to change the dynamic of our system? Absolutely. Okay? And now what we've got to ask is, what happens when I bring those near each other? How does that change the system? Okay? And that's a challenging question to get at. Okay? So Lewis went through and said, okay, well, what things would I predict to interact first? So if I take one atom and another atom and I bring them near each other, what's the first thing that's going to get encountered? The electrons. Why the electrons? What was the very first question on our quiz? Where are they located? Our protons and neutrons are in the nucleus. Right? The analogy for a nucleus, it's a marble inside the astrodome. Right? If I come up to the astrodome, am I going to first find the marble, or am I going to find the astrodome surface? Okay? The outer part is going to be the first thing I'm going to interact with. So to a first approximation, I only care about the electrons. Okay? So now the question is, which electrons do I care about? Because if we look at carbon, it's got 6. Of those 6, which matter? And if we had an electron configuration, okay, we have 2 electrons in our first energy level, our s-type. We have 2 electrons in our second energy level, s-type. And then we have 2 electrons in our p-type orbital. Of those electrons, which ones do I care about?
The outermost.
The outermost. What's the outermost?
The valence electron.
Awesome term. But of course, what's going to follow? What does valence mean?
The outermost.
Not
The
quite.
valence shell.
What is the valence shell? Energy level. Okay? So when we talk about valence shells, we're talking about the highest energy levels. Those are the ones that are most likely to encounter because they're moving all over the place. They may not be at the outside, but there's a higher probability of them encountering on the outside than any of the others, which means I only care about the highest energy level. Okay? And this is why we have to be careful with outermost, because if you say outermost, what electrons am I going to talk about?
The 2p.
The 2p. If I say highest energy level,
2s.
2s and 2p. Why do you change it?
Because the s is full. No.
What's the number in front represent?
The energy level.
The energy level. So what's the highest energy level? It's 2, which means I need to include both of those. So our valence is the highest energy level. Okay? And we could go through and deal with electron configurations and draw them all out and say, what are the electron configurations every time? Instead, what we preference is we would go through and we'd say, well, I don't care about 6, I care about 4. And if we look at carbon on the periodic table, since you have the periodic table, you can help me out. Within the P block, which column, not within the P block, counting from the far left periodic table, how many columns to get to carbon? Remember, the D block isn't there.
Well, the middle is not.
Yeah.
4.
How many valence electrons does carbon have?
14.
It has 4. It's also in the 14th column. So if you subtract 10, the D block, you get 4. All we care about are the valence electrons for any one of these individual atoms. Those valence electrons are what's actually going to start to form bonds. Okay? With that, I have to stop. I don't want to stop, but we got to stop. Okay? That little bit